An eventful day with an earthquake. So happy everybody in the room survived. And allowed us actually to go on and listen to our seminar today. So Craig Sutton is going to talk about genetic properties of Laplace Eigenfunctions in the presence of symmetry.
Yes. Okay. Well, yes. So, yeah, thanks a lot for the opportunity to speak. So, yeah, I guess I'm going to talk about some work that's actually sort of inspired by results that came out of the mid-70s. In fact, I guess Theorem of Karen Uhlenbeck, where the idea was to kind of study what are some of the generic properties of eigenfunctions, and the result there is that essentially if you have a generic metric and then you look at the eigenvalues, well, they occur with multiplicity 1 for a generic metric. If you look at an eigenfunction, for a generic metric, well, then 0 is a regular value, and then hence the nodal set is going to be a smooth manifold. And then,
what time
you didn't miss it. It just started. I just put some stuff up on the board. Yeah, okay, right. Yes, we're already in the question and answer part. So it's yeah. So your eigenvalues are going to occur with multiplicity 1 for generic metric. Your nodal set is for generic metric is going to be a smooth manifold, and those eigenfunctions are going to be Morse functions. And so I guess this project is really kind of motivated by, well, to what degree, what can you say when you're talking about metrics that actually have symmetries, where, okay, those are actually far from being generic metrics. And so what are the correct statements of these theorems, if there are any? And can you actually even say some more things than you might not be able to say if you don't assume symmetry? Okay, yes, I guess just to set the notation, I'm always going to be assuming that I'm talking about a closed and connected manifold today. I'm going to let R sub L of M be the space of CL metrics on my space. Delta G is going to be our usual Laplace Beltrami operator, and we have our spectrum, which only accumulates at plus infinity. If I have a function of the manifold, we'll let Z sub phi denote its nodal set, except for when I write it that way. So putting up there, I might switch back and forth, but at least that's what it would mean. And then I guess when we get into group actions, we'll usually just be assuming like a finite group or some kind of connected compact Lie group acting on your space. I'm going to let G hat denote the space of irreducible representations over the reals. And so all I mean here is it's just going to be some homomorphism of a group into some orthogonal group on a real vector space. And then usually throughout this talk, we're going to assume that the actions are free actions, so there are going to be no fixed points for it. And then when I have a group acting on my manifold, I can look at the space of G-invariant metrics on that manifold. Okay, so those are some of the sort of notations that we're going to use today. So, okay, so yeah, so I guess obviously for, mathematical and physical reasons, it's, nice to kind of talk about the eigenvalues and eigenfunctions of the Laplace operator. We think of the eigenvalues as representing energy levels for free particles. The eigenfunctions then kind of give us these probability density functions for where you might find this free particle, and then of course, like the correspondence principle sort of suggesting that the behavior of eigenfunctions at high energy limits are somehow maybe going to begin to reflect the underlying classical dynamics, i.e. the geodesic flow of the space. And so, okay, so the more you can say about these things, sort of the better. And so I guess in some cases you can actually do things quite explicitly. So let's say we let Sn be the round sphere. And then for every integer k, I let P sub k of Rn plus 1 be the space of harmonic homogeneous polynomials of degree k. Okay, well then from this information, we can kind of, I guess, actually sort of state exactly what's going on. So for our eigenvalues, if we ignore multiplicities, we're going to get k times k plus n minus 1. The associated eigenfunctions are just going to be restrictions of these harmonic polynomials. To our sphere. and the multiplicities of one of these guys is going to be, k plus n, choose k, minus k plus n minus 1, choose k minus 1, like that. So, okay, so those will be the multiplicities. We can kind of work everything out very explicitly. And okay, and this is sort of a special instance of a case of like if you're looking at, let's say, a compact symmetric space in general, you can, at least in principle, you can read all this information off just from representation theoretic information. So that's kind of what we're using here, or one way of approaching this. But although you can do that in principle, it turns out like in practice, it's generally not very feasible to kind of carry that out. So in general, one can't actually say anything very explicitly about these guys, but then I guess some of the work that was done in the 70s by Karen, and then I guess also Jeffrey Albert, was to kind of think about, okay, well, let's just look at what's happening sort of generically for a manifold. And so the theorem that was proven is the following. I think this is 76. So we're going to assume that the dimension of M is 2, and then we're going to let L be some integer greater than 2. We can find a set Y inside of the space of CL metrics, which is residual. So here I just mean it's an intersection of countable intersection of open dense sets, such that for any metric in here, we have the following. Well, this Laplace operator has simple spectrum. Okay, so as I said at the beginning, that just means i.e. eigenspaces of dimension 1, or that all eigenspaces are of dimension 1. 2, if phi is a non-constant delta G eigenfunction, then 0 is a regular value of phi, and then therefore its nodal set is a hypersurface. And then finally, we have that the eigenfunctions are Morse. Okay, and so actually, I mean, this result is true for more general operators, but we're just going to talk about the Laplace operator today. And so what this is saying, then basically, okay, these properties are all generic within the space of CL metrics, and then actually taking intersections and giving appropriate arguments, you can then bump this up to then saying it's actually generic amongst smooth metrics on your space. So
can you say anything stronger than residual? Or is that not true?
Okay, well, it's definitely not true. Like, I mean, like, okay, obviously in general that you can have lots of metrics with multiple eigenvalues. So I think this probably is.
But you think that's the strongest you can do? Because that can be sort of measure 0 sets, right? So
yeah,
I would think maybe there would be a stronger statement, but I don't know, of course.
I'm not aware of it. Yeah, so this is the best I know of, right? So yeah, so.
One thing you can't do, I gave it to a student, thesis and
Pardon me?
false. One thing you can't do is you might try and make the eigenvalues not exponentially close to each other.
Okay.
You try to, you say they're simple. Can you keep them lambda I minus lambda I plus 1 bigger than lambda to a big negative power, depending on the dimension, for the generic in any sense with a measure with anything? False. Schnirelmann proved an amazing theorem. There's always exponentially close multiplicities.
Okay.
Near completely integrable system.
Oh, I completely.
It's a fantastic.
That's not
Generically, and that's just false.
It's non-generic. Okay, well, great. So then,
So you really can't move the eigenvalues very far. They're exponentially close.
okay, so then, as I said at the top, I guess, metrics with symmetry are far from being generic. So we might want to ask ourselves, to what degree can, what's actually going on in the presence of symmetry? And so I guess we probably have two problems. So problem one is going to be, I guess, the intersection of symmetry with multiplicity. And then our second problem is going to be the intersection of symmetry with the structure of nodal sets and domains. Okay, so we'll start with this first one. So if I have a group acting on M, and let's suppose this action is free, that's going to give rise to, I guess, what's known as the regular representation. So it gives us an action of this group on L2 of M, where G dot F X is equal to F G inverse dot X. And so the point is that if G is actually acting via isometries, so let's suppose this is some Riemannian manifold and that's via isometries on this space. Well, then this representation here, or this regular action, commutes with the Laplace operator. So we get that G dot natural H applied to some function phi, the same thing as this guy. So what that tells us then is that our eigenspaces actually turn out to be representations of this group. So this tells me that delta H eigenspaces are representations of this group G. So then, okay, so with this in mind, the best thing that you could really hope for is that maybe that your eigenspaces actually turn out to be irreducible representations of your group. So our notion of simple in the presence of a group action is going to be that eigenspaces are irreducible. So it's a definition. So a metric that's G-invariant is said to have G-simple spectrum or G-simple Laplace spectrum if each eigenspace is a G irreducible representation. All right. And so then I guess our problem then becomes, well, is this actually a generic property within the space of G-invariant metrics?
Just one question.
Yeah.
I tried to explain, but I missed it completely. So I should not expect eigenspaces to be one-dimensional if there's symmetry.
Right. You should not.
And
Yeah.
the reason is that I see that there's an action, but still I don't see why the action should not be trivial or something.
Oh, okay. Well, okay, something. So let's suppose you have take a circle acting on take S3 and look at a circle sitting aside because that's a non-trivial action. If you look at the this regular representation, essentially every irreducible representation of the circle shows up in the decomposition. And so, okay, and so then based on that, if I pick up something as an eigenfunction, it has to be in one of these spaces. Yeah.
I mean, it's already not true. Z3, I mean, actually, I had a student who wrote a thesis on it 50 years ago. We already discovered it wasn't true in the simple group action.
Right, yeah. So, yeah, and we'll get to, I guess, some results on finite group actions in a minute, but yeah, so right, so the question, this is why you should not expect these guys to be simple. All right, so the question just becomes, well, is G simple generic in this space? Okay. So what I'm gonna do is, I guess, is maybe just, because that's how much time we'll have for method of proof, but I'll always just give like one thing that one needs to think about in terms of like attacking this problem. Is that, okay, well, maybe we'd want to have like some criteria for whether you have a G simple spectrum. And it turns out, okay, well, that having G simple spectrum is sort of equivalent to two things. So let me just.
You haven't assumed your group's non-abelian yet.
Oh, I'm assuming the group is arbitrary, it's any group I want.
So the fact that the abelian groups have one-dimensional.
Real
But
representation.
you're gonna be over real.
Yeah, I'm gonna be over the reals.
Very clever trick.
Yes, right, yeah, exactly. So, and as maybe explain later, okay, this problem doesn't make as much sense if I'm looking at complex valued eigenfunctions. So, okay, so here we go. So criteria for G simplicity. I'll say this is version 1. Not clear if we'll get to version 2, but okay. So another thing, so I'll try to, this might be one of the last, well, okay, probably won't be the last representation theoretic thing I have to say, but okay. So let's suppose I take an irreducible representation. I can talk about its isotypical component in this regular representation. And so this is then the smallest invariant subspace that contains all copies of representations of tau. Okay. And so then, so this is the tau isotypical component. And so then our space L2 of M decomposes as a direct sum of these isotypical components. And essentially by what's written up above there on that board, you can deduce then that if you have a Laplace operator that's associated to a G-invariant metric, it actually holds these spaces invariant. Okay, so you can now look at the Laplacian restricted to these Hilbert spaces sitting inside here, and then talk about, okay, well, what's the spectrum of the Laplace operator restricted to those?
I'm sorry, the isotypical component is the space of functions that are tau invariant.
Basically, yeah, it's a small, yeah, right. So that's, yeah, that's one.
That, or it's almost that.
That is that, yeah. And when we, it'll be exactly true when I sort of switch to like a vector valued version of it. But yeah, there's this space of functions, and they all sort of transform according to this representation. Tau, yes. Okay. So then, what we see then is that this guy holds this guy invariant. And so then with that in mind, we then get to criteria, which maybe explain a little bit how one might approach the problem. So a metric inside here has G simple spectrum. If and only if the following things are true. Well, one, we want to have disjoint isotypical eigenvalue sets. Okay, so what do I mean by this? I mean, if I take two inequivalent irreducible representations, and then I look at the set of eigenvalues of this guy restricted to this isotypical component, okay, that should be empty. So if two different isotypical components shared an eigenvalue, okay, then this theorem would be false. So okay, it certainly has to be separate. So you have the separation along isotypical components. And then the next thing would just be that on each isotypical component, you actually need to have this G-simple spectrum. So 2. So we'll call this G-simple isotypical Laplace spectrum. And so it's just what I said. If I take an irreducible representation, then the eigenspaces of the Laplacian restricted to that isotypical component are irreducible and necessarily equivalent to this representation tau, because those are the only finite dimensional representations inside that space. Okay, so if one is going to sort of try to prove this result, most strategies, or maybe all strategies that have been employed so far, kind of use this, and there's sort of these two components to it. Okay, so then, and so what you might want to do is you can, and even if you fail, you can maybe succeed at one, and just show that one of these is a generic property, but maybe the other one turns out not to be generic in some settings. So let me now, I guess, maybe just talk a little bit about what's known regarding this problem. So as far as I could tell, maybe one of the earliest results on this is this result by Zeldich, sorry, and Karen's student's thesis notwithstanding. So let's suppose you have a finite group acting on a space, and let's suppose that space satisfies what's called this high dimension, low degree criterion. So that means that the dimension of your space has to be at least as large as the largest irreducible representation of your finite group. Okay, finite groups top out at some point. So there's some lower bound on how big your manifold can be. Well, then it turns out that G-simple spectrum is generic within the space of G-invariant metrics on that space. So maybe one could just be thinking here of like a regular covering space or something like that, right? Okay, another place where this problem showed up is...
There's one question. So
yes,
just understand this criterion. So this criterion that you have given us, like once you are stating it, it's very easy to show that then it implies G-simple stuff. Right. You're just saying that the spectrum is splitting over different isotypical components, and then you are telling us on each component, right, it's irreducible. Right. Okay, just understand that. Okay.
Yes, exactly. Yeah, you got it. Okay, so so now another variant of this problem, so one could, let's say, well, let's look at the space of left-invariant metrics on a compact Lie group. So instead of looking, so this is now transitive action, so that's the finite dimensional problem. So this problem up here, the first one's infinite dimensional space of metrics. Now we're looking at a finite dimensional space of metrics.
What was Yale's problem?
Oh, so Yao, oh, sorry, I didn't say that. Yeah, so Yao actually stated this problem as one of on his problem list. So that's another place where we were able to find this in the literature. So then I guess Gilliman at one point was interested in this question. Okay, so we have a compound. Oh, yeah.
What is the problem of Yao?
Oh, the one that we're working on here, that whether some G-simple spectrum is generic. Yes, sorry for that. Yeah.
And the previous theorem, so you are giving us a condition that has two numbers and only one depends. So one depends only on the group and one depends only on the manifold.
Right. So once I fix the group, yeah, then it tells me, okay, I can only be talking about manifolds of a certain dimension. Right. Okay. Yeah, exactly. So then, okay, if I look at this sort of finite dimensional problem, okay, she attacks it sort of the same way and is able to derive algebraic conditions. So turns these statements here into algebraic conditions. And it turns out, well, okay, I've written it here for products of S3s with tori. There are a few other groups, but essentially she has criteria written down and can only show that they're verified in some very limited cases. And so, but in those cases, you can then show that, okay, well, this idea of having G-simple spectrum is generic amongst left-invariant metrics, but it's not known for, well, basically almost all simple Lie groups or any semi-simple guy.
The manifold here would be G itself, right?
Yeah, so the manifold here is G itself. So G is acting on itself by left multiplication. Right. So yeah. All righty. So then I guess another variant of this was that, okay, one can look at, let's say, trivial G bundles. And so Gomez and Morocco sort of came up with criteria for when those trivial principal G bundles would have this property. And it turns out, okay, you can then, the groups for which Schuth succeeded in proving her result is true all satisfy the criteria in their theorem. So the result is essentially insert groups from her theorem and you get that it's true. And so then I guess then maybe a little more recently, the result of Jung and Zeldich, which says, okay, well, let's look at a principal S1 bundle over a surface. And now let's look at the S1 invariant metrics on that manifold. Well, then it turns out, okay, that they're actually generic. And actually here, it's a stronger statement because I can actually look at the Kaluza-Klein metrics. And so a Kaluza-Klein metric, so if I have this S1 bundle, those are metrics where the S1 orbits are actually geodesics. So that's a smaller subset in the space of all S1 invariant metrics. But then once you know it's true within the space of Kaluza-Klein, well, then you can actually then get that it's true in the space of all S1 metrics just by perturbation. Okay. So, okay, so that's sort of what's known, and I want to now state our result on this. So let's see, what can I erase?
Sorry, you gave a sufficient condition in the Zeldich theorem up top there. What about false otherwise?
It's unknown. Yeah, so it's more, it could be that
Is there a counterexample?
there is no counterexample to this. I'll say that like a similar thing. So, okay, so I'm going to state a result.
Maybe that's what Karen's saying, that a student, I'm trying to follow what did you say, Karen, at the beginning? That your student had a counterexample to what?
Well, I'm sorry, it was so long ago, I can't remember. I remember that she actually explicitly computed the eigenvalues of a equilateral triangle at some point, but we discovered that well, I know it's pretty clear. If you have a space where the representations where the non-trivial representations appear, you're not going to get rid of them by perturbation.
Right.
I mean,
You're insisting that they preserve.
Yes,
Right, but
that's not a
you're saying, but it may be true that you can make everything as simple as possible according to what the symmetry dictates. And without that condition of the.
Right, and it's still in, that still seems.
Yeah, that sounds interesting.
Right. And so, so what you'll see is, so I'm going to state a result about tori acting on manifold. And, okay, now tori, as you point out, okay, well, if it's the irreducibles over the complex, they're one-dimensional. Over the reals, they're two-dimensional. And so we'll get kind of like a maximally strong result in that setting. But then if you start to think about this for arbitrary, let's say, compact Lie groups, you will start to kind of run into some issues that are similar to what Zeldich ran into over here in this.
The fact that this finite is important. For compact, it's Zeldich didn't prove it.
Well, right, yeah. So if the finiteness part just sort of tells you, okay, well, there's some upper bound on the size of your dimensions of your representations. But yes, you're pointing out for an arbitrary compact group, you have ones in arbitrarily large dimensions.
No, but if you take a compact group for which the dimensions are bounded, that's the theorem still.
So that might be true. That like if you say, okay, let's suppose I look at representations up to a certain dimension, and then so maybe I'll state the theorem and I can kind of then tell you some possible variants, something like that. Okay. All righty. So all right, so here's the theorem. Yes. So we're going to let T be a torus of dimension D, acting freely on M, and with the quotient space of dimension at least 1. Then for any integer L at least 2, T-simple spectrum is generic in the space of T-invariant metrics on N. So maybe I'll give a few examples, and then I'll just talk a little bit about, maybe address some of the comments that were made.
Sorry, what's L? Integer L, what's the?
Oh, sorry. L is the space of CL metrics. Thank you. Yeah, right. So then, so here's an example. We can look at, let's say, the hot bundles. So here we have S1 inside S2n plus 1, which then projects down to CPN. So, okay, so I can now look at the space of all S1 invariant metrics on the space. And that turns out, if I look at that space, that T-simple, S1 simple spectrum is a generic property. Obviously, the round metric, the one we started out with at the beginning of the talk, does not satisfy this property. But if I'm looking for a generic S1 invariant metric, I do get that it's true. Let's see, 2. You could look at, let's say, 2-step nil manifolds. And so here, I guess the thing to point out is that your 2-step, if and only if you're a torus bundle, a principal torus bundle over a torus. And so here we have TD inside M, which then projects down to this guy. And so in the space of all torus invariant metrics on M, it turns out that you get that your for a generic metric, your eigenspaces are going to be irreducible representations. Okay. So, okay, all right. So I guess this is also the mathematical physics seminar. So I'll just make this one comment that, so another place where this problem, I guess, appears, I know there was some textbook that we found by Wigner, and he talks about this idea that, okay, well, for physicists, this idea of like when you have sort of multiplicities, when your eigenspaces are not irreducible, they kind of consider these to be accidental degeneracies. And so the point here then is that this is kind of like a mathematically rigorous statement of that. So, all right, so there's some connection there. And I guess it's also kind of interesting because then, although maybe you have these accidents that are occurring, a question we could ask is, well, okay, are there some kind of like hidden symmetries that sort of account for why your eigenspaces are not irreducible? So maybe there are like some constants of motion that you could use to kind of show, okay, that's why you're getting these extra multiplicities in these examples. So I do think that could be kind of an interesting problem for people, to think about. Right, so I guess, yeah, people like asked a few different questions about things. So here, one of the things that's going to help us in the argument is exactly the fact that for tori, irreducible representations are of dimension 1 or dimension 2, and that kind of helps us to avoid this situation we had over there for Zeldich. If one were to kind of look at sort of arbitrary compact Lie groups, the argument that we used, it certainly come to points where you would probably have to put some kind of restriction on the dimension. You say, okay, well, I just want to look at representations that are no larger than the dimension of the manifold, and then one might be able to still make some of the arguments go through, but it still wouldn't show it for all representations. But I guess I'll maybe put a pin in kind of like going through the argument for that, and I then want to kind of like pivot to the second problem, which is then sort of talking about structures of nodal sets and nodal domains. Okay. So, all right. problem 2. So this is the symmetry and structure of nodal sets. Okay, so right, so obviously, I guess nodal sets have been studied at least since the 18th century when Chladni was sprinkling sand on plates and looking at these nice intricate patterns that you get when you excite the plate at various frequencies. But on the other hand, I guess we also know that, okay, well, without restrictions, Whitney has proven that, okay, well, if you take any closed set, you can always make it the nodal set of a smooth function. But in the case where you're looking at, let's say, Laplace eigenfunctions, okay, we do have a little bit of structure. So we know that, so I think this is Hart Simon from 89, that if this guy is an eigenfunction, okay, well then its nodal set, we can look at the points where phi of p is 0 and the gradient of phi at p is non-zero. And then that's a disjoint union with the places where it's singular. And the point is that, okay, well, this part here is an n-1 dimensional manifold with finite measure. And this set here is going to be a countably n-2 rectifiable set. So then I guess another way of stating, I guess, the second part of Uhlenbeck's theorem is that for a generic metric, this part is empty, and you're just left with sort of this manifold part here. I guess another definition that we'll need is that of a nodal domain. And so we'll let, I guess, a connected component of the complement of a nodal set is a nodal domain. And it can be of interest to study, I guess, okay, what's the structure of those? Like, how many do you have, et cetera, et cetera. So I guess the question that we'll be interested in now is like, well, one, can we show that under group actions that these nodal sets actually are still hypersurfaces as they are in the case that Karen considered? But then we actually kind of want to ask, can we get a little bit more out of that by exploiting symmetry? So in the statement that we had at the beginning, okay, you could have a manifold, but could actually have lots of different components. What we're aiming towards is, well, can we show that generically these are actually just connected manifolds? And then if they're connected, you can then ask, okay, well, how many pieces does it actually break your space up into? If it's a non-constant eigenfunction, it has to break it up into at least 2. And of course, Courant's nodal domain gives you an upper bound. So what we're going to be able to show is that actually for generic metrics, you can actually always get a lot of eigenfunctions with exactly 2 nodal domains. Okay, so that's where we're headed. So maybe I'll give a little background. So, right, so I guess I just said that in general, if you have a Laplace eigenfunction, we know, and it's non-constant, and if I let n of phi be its nodal count, well, then we know from the nodal domain theorem that this is just bounded above by this guy here. There's a result. So one thing you might wonder about is, okay, well, can you actually have lots of eigenfunctions that maybe saturate this upper bound? So it's a result of Weyl, maybe from 56, and then I guess Bernard, and Meyer, and I think this is 84, which basically shows that, okay, well, that the lim suit of this divided by K is always bounded. If I'm in dimension n, there's some universal constant which bounds this lim sup, and it's less than 1. So I've shown, okay, well, in general, you're not going to get lots of these Courant sharp eigenfunctions. Okay, so any orthonormal basis will have sort of finitely many eigenfunctions which saturate this.
I think Gauguin has a world record.
What's that? Oh,
Gauguin improved on this, at least in dimension 2.
okay, but
He has a world record.
okay. Let's see. So then another result that's of interest. Maybe regarding, I guess, the number of nodal domains. Okay, I'll skip a few here. And maybe talk about Zhang and Zheng. So this is from 2018. So if sigma H is a surface possessing an orientation reversing isometry tau, so that the fixed point set of tau separates sigma, then and say, I guess, and we have an orthonormal basis of eigenfunctions satisfying quantum uniquity. So QUE, then it turns out that you can find that this nodal count has to go up to plus infinity. So in some cases, one is actually sort of able to produce these sort of like large families of eigenfunctions where, okay, your nodal count has to be flying off to plus infinity. You can then also sort of look at the other end, and that's kind of what I was foreshadowing, is like, well, what about the other end? Can you actually produce examples of eigenfunctions where you always have like sort of the minimal nodal count? So I think through like some ad hoc methods, there were some examples in the 70s by Levy on the sphere. And then I think there's also a thesis of Stern from like the 20s, which also produced some examples. I'll just talk about the examples of Levy, though. So this is 1977. So there exists a sequence plus J of spherical harmonics where the degree of psi j is j, and the nodal count for the even degree ones is 3, and the nodal count for the odd degree ones is 2. But this space of eigenfunctions sort of spans a density 1 subspace, a subspace of Weyl density. I'm sorry, 0. So okay, so yeah, right. Okay, so it's kind of
make many of it.
yes, right. So okay, so they're kind of sparse in this space. So I guess I'll come to the statement of the hour theorem then.
But it's much worse than this. So I think it just constructs a sequence.
Okay, so maybe just
one in each harmonic.
Okay, so maybe, all right, I tried to upgrade it, but all righty. So
Not giving you an orthonormal basis.
I see. Okay, so let's see. So here's the theorem. I guess we'll let TD act on M freely. we'll let V be this quotient space and L an integer greater than 2. So the first part is that if the dimension of B is greater than 1, there is a residual set Y1 sitting inside our space of L-invariant metrics, of CL metrics, such that for any G inside Y and be a non-constant eigenfunction, then 0 is a regular value. Of phi. So, okay, so in particular, we're able to recover that second statement of Uhlenbeck's theorem in the presence of symmetry. But like I said, I guess what we would like to know is a little bit more. Like, okay, can we say something about the topology of the space? Is it connected? And then how many components does it actually break our space up into? So if we now assume the dimension of B is at least 2, so it's a cohomogeneity, at least 2 group action, and for each alpha not equal to 0 inside CD, so to each set of integers, I'm going to associate some kind of circle bundle sitting over this space. And I'll explain in a second like where this bundle comes from. So this is a natural associated circle bundle. And let's suppose this guy is non-trivial. For any choice of integers. And there exists a residual set in here. So that for any non-invariant eigenfunction, phi, Z sub phi is connected and the nodal count is exactly equal to 2. So now why does this lead to lots of examples of these?
One question.
Oh, sure.
Without the presence of symmetry, you have not showed us a statement of a generic result about the number of components. Is there something like that?
I'm not aware of like that. Yeah. So the results I'm going to see today are kind of like it's the first one that I'm aware of that kind of tell you.
This is a very
about
beautiful question.
Yeah.
I think it's very different. I mean, there is a theorem about a random spherical harmonic that's due to Sutton and Nazarov.
Yeah.
That it has a growing number of components, but not an orthonormal basis.
So you're saying that a random spherical harmonic, random in a certain sense, I should expect
Random, yeah, Gaussian random, they proved a remarkable theorem that it's got a growing, it's got Courant type constant times the.
Oh, so it's growing linearly.
Fraction of the maximum, yeah.
Oh,
But that's in dimension 2 and in n dimensions, but the issue, well, we'll get to this.
Right. Maybe I'll say then, okay, so this is sort of a condition. So we need to have the presence of some non-trivial circle bundle. So maybe explain how these circle bundles arise and then give us a topological condition for knowing that we actually have them, and then talk about why we get lots of these examples. So what is this circle bundle? Talking about, so
Sorry,
uh-huh.
you need dimension be greater than 2, yeah, that's very important.
Yes, right. Yeah. So this is
But and what did Zeldich and Jung do with another? It was a client.
so here, right. I was gonna say something about that after saying this, but yeah. So right. So they also have this for their Kaluza-Klein metrics as well. So basically, there are two results I'm aware of: the Jung-Zeldich results and the results they did with CNC, Judge, and Lim. So let's see. So let's suppose you pick a non-zero tuple, and let's consider E alpha and so I have that T is acting on R2 according to theta goes to rotation by alpha dot theta. Okay, so let's suppose that's my action. So I have a group, this torus acting on a manifold M. For every D tuple, I get a representation of that torus on R2. I can now look at this trivial bundle, and then I can let T act on it and take its quotient. And that's going to give me a vector bundle over this quotient space here. So then what I can do is I can sort of remove the zero section from this guy and then scale by the positive reals. And I'm now going to get a circle bundle sitting over this space. Okay, so let's remove the zero section of E alpha and scale by R plus to get a circle one. Okay, so then, so the way this is used is, so I guess the technique that's behind this is that we kind of need to know that we have eigenfunctions that don't vanish on orbits. And what we're sort of doing here and kind of hiding is that this construction here is a way for us kind of like testing whether we actually have the possibility for functions with that property. And so corollary here, we're going to say topological condition for when this is true. Oops. So let's suppose corollary. Let's suppose that our quotient space is closed with dimension at least 2. And let's suppose that the second cohomology is torsion free. And so now let M over B be a non-trivial S1 bundle. Then for any S1 invariant metric, on M, each equivariant yet non-invariant eigenfunction phi has exactly two nodal domains. And so I guess an example of a case where this actually holds, we can go back to our Huff bundle again. Okay, and so this is satisfied in this particular case. And so here we'll see, okay, that we actually now get these eigenfunctions with exactly two nodal domains. And I guess the point with it sort of like being density 1 is that it goes back to our decomposition of our L2 space, which is that we have first the invariant functions, the ones that are in sort of the trivial isotypical component, and then there's sort of everything else. And okay, these guys here form a subspace of Weyl density 1. So then basically, when you have one of these metrics, your eigenfunctions, your non-invariant eigenfunctions live in one of these isotypical components, and they all have sort of exactly two nodal domains. So I'll just say that, so Jung and Zeldich, so the second part of their theorem is essentially exactly the same statement, but it's that case, it was kind of restricted to dimension 3. They do have a preprint, I think it came out last summer or something like that, where they are now to look at sort of arbitrary S1 actions on manifolds. I guess here we're kind of stating ours for arbitrary torus actions. So there's that difference.
Right, where's the generic condition or the?
Oh, I'm sorry. Yeah, right. I guess that's up here in this.
Yeah, but in this statement.
So here, let's see. Right. So this part is now telling me that I have that all these associated bundles will actually be non-trivial, and so then therefore I can apply this theorem, which tells me there is a generic subset which has this property.
So you still have to make a generic metric.
Says for any S-invariant metric, but it should be for some residual.
Oh, I'm sorry. Yeah. I'm sorry. Yeah. Thank you. Yeah. I'm sorry. Yeah. Sorry. Thank you. That's, yeah. Yeah. So for a simple set of S1 invariant metrics. Okay. Et cetera, et cetera. Yeah. Sorry about that. Yeah.
Can you find, so have you been able to make an orthonormal basis?
Yeah, so these are, I mean, so.
No, the bottom one, except the two nodal domains.
Right.
You would have the invariant guys which now live on the base.
Right.
In 3 dimensions. Then I'm in 2 dimensions.
Right.
And can you arrange that to have 2 nodal domains thus?
We can't arrange that.
Okay, so you have to remove those guys.
Yeah, so right, so this is really just a theorem about what's happening over here. And we still have sort of this density 0 space where you could have lots of nodal domains. Maybe they are going off to plus infinity. We don't know. And yeah, we don't really have a way of controlling that. So, so anyway, okay, I guess I'm like sort of at about 1 minute. So maybe we'll stop here. And yeah, I think.
Questions? My memory was that Jung and Zeldich in these Kaluza-Klein, I thought they made an orthonormal basis of, or not, of eigenfunctions which were exactly, each one of them had 2 nodal domains. I mean, just the existence of that is remarkable.
Yes, I mean, so I think their results are sort of the same in that, yeah, you can form an orthonormal basis over here, but they still can't say anything.
Oh, they can't say anything on that?
Yeah, they can't say anything there. So, right, so I think all these techniques run into the same.
Yeah, so if you took a planar domain,
yeah,
dimension 2,
mm-hmm.
and try and create just 2 nodal domains, it's going to be extremely hard. I mean, I'm not sure it exists.
Yeah, I don't, right, yeah.
So I think there's something between dimension, because this is really separation of variables through this S1 action. And then the guys which are non-trivial are glued in such a way that
right.
They're forming just, all the components are connected now.
Right, exactly, yeah, so they kind of like twist up and get
But
connected.
in dimension 2, you have no.
You can't. Yeah, so like the argument we give, you run exactly into like, it's just something you cannot do in lower dimensions. And so one would really have to take a different approach if it's even, yeah, possible, which, as you said, might not be.
So, yeah, no, I might make one comment because this question was raised. If you take a random function, dimension 2, what this Sutton and Nazarov showed, you take a random function or a random monochromatic wave, it will have many components, but they're very small little components. In dimension 2, that's sort of what you see. But if you go to dimension 3, there's this giant percolating component, which eats everybody up. So in fact, in practice, you will just always just see two components, even though there will be a little fluff of small components with very high frequency. But this giant percolating component, so there is even at the random level, a fundamental change from dimension 2 to 3.
Hey, you're talking about the round sphere?
Take the round sphere with random spherical harmonic and ask how many domains does a high degree polynomial have, and it'll have many components that they proved. Those components, you'll never see them because there's going to be this one giant component in dimension 3 that numerically, that's all you ever see. I can show you pictures. You just see nothing else. It just eats everybody up.
Right.
So you have this super critical percolation regime. And it's been proven by Hugo Copan and his colleagues.
Yes.
Well, actually, was it really important to use real representations?
Oh, well, okay. So for the multiplicity result, yes, because it's not true.
I didn't understand. I think Peter said something.
Yeah, well, okay. So even like in the so just take a compact Lie group and like with left invariant metrics. Okay, so you can write down like what the Laplace operator should be in terms of your Casimir operator, and you can then see if you're looking at you know, a isotypical component that's of complex type. There, what the issue is going to be is that, so those guys are not self-dual, but you can prove that for any left invariant metric, I'm not able to compute it explicitly, but you can prove that they will always have exactly the same eigenvalues. So therefore, you will always have on these two different isotypical components, they have to. So you have to modify the conjecture there, and maybe it's something like, okay, it's irreducible when they're real type or quaternionic, and then when they're a complex type, then you might get
Two pairs.
right, these pairs or something like that. Maybe I don't even know. Maybe that's clearly false. But this is not true.
It's definitely right.
Yeah. So yeah.
The freeness assumption that the group of 3 is it important for the problem 1?
Not yeah. So right. So we're working on I guess removing all of that, and so yeah, we think one can get rid of that assumption. For the nodal domain part, okay, that gets a little trickier. Like what's really going in there. So, but I will just say yes. So for the multiplicity part, we're pretty confident we can remove that. And then you know whether you can do this for you know arbitrary compact Lie groups, as you're sort of alluding to before. Like I said, I think one might be able to do this with sort of like some kind of like high dimension load, you know, just capping off the dimension and saying as long as the space is at least the dimension of some representation.
So actually abelian groups.
Well, no, so now this is just any compact group. I mean, there are some things like in the argument. So like I think so there was like two pieces. There's this whole separation business, and there was the simplicity on an isotypical component. The separation business, I think, still deals like. Think there's a good chance that that's just kind of just true for any compact group, but it's really in this other part about whether you have simplicity on isotypical components that might actually be a problem. Right, and I should also say, so yeah, we're talking here now about Laplacian, but you can also talk about lots of other eigenvalue problems and start to apply these same techniques in other areas where you might want to know things about nodal sets, and so we're also kind of doing that too. Yes.
If I got it right, this is open, but I'm not even sure I understand what would be the conjecture. So if I take a generic metric on a nice manifold, compact and everything, do I expect all of the nodal sets to be connected or not?
No.
Oh.
Yeah, I don't think that, yeah. Maybe some other people have ideas on that, but I don't, yeah.
So do you get any results, special for discrete groups? I mean,
Yeah, so we didn't look into the discrete groups because I guess we really wanted to, yeah, we were trying to leverage perturbations as much as we could. And so with Lie groups, we had a lot more to play with in that setting. And so, yeah, so we haven't looked into that. And so, yeah, so like for the cases we did study, you know, you have like basically your space of metrics is controlled by the base, what's happening on each fiber, and then by your connection form. And we have to kind of leverage perturbations kind of like in all of those different ways to get these results. Yeah.
Okay, there are no more questions. Thanks. Perfect.